So we've seen several forms of mechanical work of force times distance with springs and gravity, for example. And so now let's turn our attention to an interesting form of work that is done by gases. There was a project in Make magazine many years ago, and you would 3D print a rocket. It wasn't really a rocket, but you'd mount a GoPro in it and then put it into some PVC tube. It fit nicely, and you'd have a PVC tank. You pressurize it with compressed air. You had to use the right kind of PVC or it would explode, so it could be dangerous. But once a diaphragm broke, that would allow compressed air in behind the projectile, essentially, and it would shoot up and out and go a nice distance. There were some wings that would come out, or stabilizers, I guess you'd call them, on the back of the projectile, and it'd sort of rotate a little bit, so the GoPro would have a window on the side and would kind of get a view around as the thing went through the air. It was an interesting project and a lot of fun. But if you think about what's happening inside of that tube, it's kind of like the barrel of a gun with a bullet in it. Okay, so what happens is there's compressed gas behind that projectile that expands. Now, as it expands, it's pushing the projectile, and of course the pressure in the gas goes down. So the question becomes, all right, if I've got this essentially piston moving through the barrel of the cylinder, and I've got a gas behind it that's compressed, and that gas is expanding, how much work does the gas do on the piston? Because of course the pressure of the gas is decreasing. So let's consider a piston being moved from state 1 to state 2, and as it moves along, say a differential distance ds, the gas pressure is going to decrease a little bit. So let's analyze this and see what we can come up with. So we've got force and we've got distance. Force times distance is work. Even though that distance is a differential distance, the product of the two is certainly work. And so the boundary work in going from state 1 to state 2 would simply be the force integrated over the distance. Because understand that force comes from the pressure, and the pressure is changing, so the force is changing. The force is decreasing. Now understand, we're assuming that there's no friction on the sidewalls and that no gases escape around the sides of the piston. Now that's an important assumption. It means that this system is reversible, but we'll talk about that in a subsequent chapter. For right now, what you need to know is that this is a perfect piston cylinder device, and the gas is doing work pushing the piston up. So we'll plug in the force, we'll plug in the differential distance, and integrate between the two states. Okay, well, what else could we consider? Well, the force is generated by pressure in the gas, so the pressure of the gas times the cross-sectional area of the piston should be equal to the force, since there's no friction on the sidewalls. So we can make the substitution that the force is equal to pressure times area, and you see the substitution in the equation there. Now, if we think a little bit further, the cross-sectional area times the differential distance is the differential volume change of the gas, right? So area times that distance is dV. And if we make that substitution, then we end up with an equation that says that boundary work is the integral of PdV. And this is really important because we've gone from some force that the piston is pushing on whatever it's pushing with and distance. We've gone from that to properties of the gas, to pressure and volume of the gas, and that's a really important transition. Now, we had to make some assumptions along the way. For example, that this was a reversible thing, but this is where we are. So now, all of that is great, but here's what you really need to know. Boundary work, the work done by a gas as the gas expands, is equal to the integral of PdV. Now, this is the non-integrated form, right? This is the integral form. I will not have you integrate this. I will integrate it for you several times, and I expect you to write them down in your book in the summary. This author has a really nice summary at the end of every single chapter before the problems are presented. I would highly recommend you tab all of them as we go, and especially starting here in chapter 3. So if we think about what this means, let's take our piston cylinder device, let's turn it on its side so that now as the piston moves to the right and the volume increases, it's essentially following a volume axis. Well, if the volume of the system increases a little bit, that's a differential change in volume. And if we multiply that by the pressure, well, we already know that's a differential amount of boundary work. So you see the pink shaded area there representing a very small differential amount of boundary work. And so that area under the process curve represents a differential amount of work. And therefore, if we want all of the area underneath the curve, what are we asking for? Well, we're asking for the integral of PDV, which is the total amount of boundary work done by the gas during the expansion from state 1 to state 2 as the pressure drops. Okay? So the area underneath the curve on a PV diagram for a process curve, a process path, represents the total amount of boundary work done either by the gas or on the gas. Now notice that the symbol in front of that boundary work for the little pink area is a little Kronecker delta. It's a really strange little symbol. It's really a D in Greek. It's not something you see very often. Why didn't we just put a D there, since it's a differential amount like we did with volume, right? We've got a little D in front of the volume, and you understand that means a differential change in volume. Well, the reason that it's a different symbol is because the boundary work is not a function of the system. Okay? The boundary work depends on the process path. Just like we saw before, depending on what path the system takes, the amount of work done by the system or on the system will vary. And so there can be multiple different process paths that involve a differing amount of work. We can have a process path that encloses more area, and that process path then represents a higher level of work interaction, a greater magnitude of work interaction. So our basic idea here is that if we could have a system where we put a small amount of work into it but get a larger amount of work out of it, by going on a cycle, then we're back where we started. We can run that cycle over and over again and produce a net amount of work. So the forward process in this case is something that generates more work than the reverse process, C, consumes, and we generate a net amount of work by operating this thermodynamic cycle over and over again. You might look at this and say, well, wait a second. Number one, this sounds like you're trying to make energy out of nothing, and you've already said that perpetual motion machines don't exist and can't happen. Number two, is there any practical place in the real world where this could be used? Well, actually, there is. The answer to both of those questions is that this already exists. Now, it's not making energy from nothing. Let me give you the practical example. If you think about your piston cylinder engine that probably pushes your car down the road. Most of you probably don't have electric cars yet, and that's fine. What happens during the process is that the piston compresses an air-fuel mixture. Now that air-fuel mixture burns relatively rapidly, and then the gases above the piston are at a higher pressure even than after compression, and as they push the piston down, they generate more work than the piston used pushing the gases and compressing them. Okay? So the forward process is the expansion, or what's called the power stroke, and that generates a whole lot of work output, right? Because the gases are really hot. But then we bring in some fresh, cold gas, and I don't mean gasoline, I mean air, and gasoline mixture, and we compress it, but since it's already cold, yes, its pressure and its temperature goes up, but it doesn't take as much work to compress it as what we're going to get out of it when we burn the air-fuel mixture. So this is already the compression stroke and the power stroke in your car's engine. And we're not generating energy or creating it from nothing, because it's the thermal energy from burning the gasoline in the air that is transformed into the excess work. Okay? So depending on which paths we choose, we can get more or less energy out of one cycle, because we can choose different process paths to move along. Now there are special cases of boundary work where we will want to evaluate them quickly and easily. In translation, you probably don't want to integrate the boundary work equation every time I give you a boundary work problem. So let's look at some special cases where I can give you the integrated form. Basically, we just need cases where the pressure and volume relationship is known, because if the pressure is known as some function of volume, then the shape of the process path is determined, and therefore the area beneath that shape, in other words the boundary work, is also determined. So let's consider the special case of a polytropic process. You might look at this and say, well, it kind of looks like an ideal gas equation, PV to the N equals C, where C is a constant and N is a constant. Well, this is not an ideal gas equation. It looks like it, but it's not. It is related to ideal gas, but we'll approach that later. This is an equation that could apply for real gases. It depends more on how the gas is expanding and the particulars of the expansion or compression process that determines whether or not it's a polytropic process. In short, I would have to tell you if I'm giving you a problem that is a polytropic process problem. Now, I might tell it to you in a sort of sly way. For example, if I give you the pressure to diameter, let's consider the system as just a sphere, okay? If I just give you a sphere like a balloon or something, and I tell you that the pressure and diameter of that balloon are related, and I give you an equation to relate the two, I may have just given you a polytropic equation, because diameter and volume are related to one another, right? At least for that sphere. And so you could ultimately come up with a relationship between pressure and volume, and that relationship may be a polytropic relationship. So you may have to work with the math a little bit to figure out if I've actually given you a polytropic process. The second question students ask is, okay, do we look up these constants N and C somewhere for particular gases? Well, the answer to that is no. I would have to give you those as well, or give them to you in, again, a sly way. Now let's consider a polytropic process and try to figure out what the boundary work would be for that process. So the polytropic equation is PV to the N equals a constant. If we rearrange it, we can put the pressure on one side and the volume on the other, and write P equals some constant V to the negative N power. And now we can substitute for the pressure in the boundary work equation as CV to the negative N. So we're at about the second equal sign on the second line. So we've got the integral from state 1 to state 2 of the pressure, which is CV to the negative N dV. If you remember your rules of integration, you might remember x to the n dx, the integral of x to the n dx. That's the rule we're using here, and I'll let you review it and see how it applies if you wish. I'm not going to go through those details. But once we integrate v to the negative n, we end up with v to the negative n plus 1 in state 2 minus v to the negative n plus 1 in state 1 over negative n plus 1. Now c is a constant. It came out of the integral from the very beginning, so it's just there as a multiplier. Now on the last line, if we distribute that multiplier c throughout the two terms in the numerator, then we have something that looks almost like the equation at the top, P equals CV to the negative n, except now we've got a plus 1 in the exponent. So if we then separate out those two exponents on the volume, so we've got V2 to the negative n plus 1, if we separate that out, and you remember your rules of exponents, that's the same thing as V2 to the negative n times V2. But now we have exactly what we have in the first equation, and we can replace CV2 to the negative n by the pressure in state 2, and we can replace CV1 to the negative n by the pressure in the first state. Also, we flipped around the order in the denominator, so we have 1 minus n rather than negative n plus 1. Now, all of that is great. If you understand the calculus, you follow the math, that's fine. You may have to pause the video and look at it to understand it. But here's what's really important. The boundary work for polytropic processes can be calculated by this equation that's in the box. The only caveat is we can't calculate the boundary work when n is equal to 1, because look, the denominator would blow up. That doesn't work. Now, if not only is the gas behaving polytropically, or it's a polytropic process, but also the gas is behaving as an ideal gas, then PV equals MRT, and we can substitute for PV in the boundary work expression by MRT. And of course we'll factor out the mass and the gas constant, because the mass in the system, it's a closed system, so the mass is remaining constant, and of course the gas constant is constant. But we still have the same restriction on this equation. As a matter of fact, we have more restrictions on this equation than we had on the first, because now not only does the gas have to be polytropic for this equation to apply, or the process has to be polytropic, the gas has to be an ideal gas. And again, this still doesn't work if in the polytropic equation describing the process n is equal to 1. So you should write that equation, or both of them, into your text. I think the first one with P2 V2 minus P1 V1, I think that one's already in the back of the chapter in the summary, but the one for ideal gases may not be there. So polytropic ideal gases may not be there, and sometimes it's more convenient to use than the P2 V2 minus P1 V1 equation. Now, just like any other time, when you see, oh, we can't do this, we can't investigate that, where do you want to investigate? In that area, right? So what the heck happens when n is equal to 1? Well, then the integration is just a little bit different. So if n is equal to 1, but the process is behaving PV equals C, then can we use this equation? No, because it's understood that the exponent on V is a 1, and that doesn't work. What can we do then? Well, it turns out we end up with the exact same form of the equation if we have an ideal gas at constant temperature. So unlike the last equation, which was mR quantity T2 minus T1 over N, or 1 minus N, instead of that, we now have a situation where we can have either a polytropic process with n equal to 1 or an ideal gas at constant temperature, and the equation we develop will work for both. Why would that be? Well, if we have an ideal gas at constant temperature in a closed system, then again the form becomes PV equals C. It's the exact same mathematical form as a polytropic process with n equal to 1. In that case, the pressure can be replaced by the constant over the volume, and now we have a form of 1 over x dx. And if you remember how you integrate that, it just becomes a natural logarithm of the variable, so the natural logarithm of the volume in this case, evaluated from state 1 to state 2. So that's c times the natural logarithm of v2 minus c times the natural logarithm of v1 if we distribute the c. But from our rules of logarithms, you may or may not know this, you may not remember it, when you have two natural logs, one that's subtracted from the other, you can put the argument of the negative term into the denominator of a fraction, and then the positive term argument goes in the numerator. So if you remember this, great. If you don't, it's okay. And we can replace that constant C by the product PV, either in state 1 or in state 2. I've just shown state 1 here, so P1 V1 natural log V2 over V1, or you could write P2 V2 natural log V2 over V1. I don't think this is in your text, so I would suggest that you write it. In the special case where we have a polytropic process with n equal to 1, or we have an ideal gas at constant temperature, there's the integrated form of the boundary work, and you should make a note of it and the restrictions on it. What are the restrictions? Well, you either have to have a gas that that is ideal at constant temperature, or you have to have a polytropic process with n equal to 1. Then this equation will work for calculating the boundary work.